We have now discussed a bunch of different ways to extract zeros from the various forms of a quadratic. The next thing that we have to do is talk about some of the other terms and concepts that are related to zeros. We introduced the idea of some of these synonymous terms and concepts back on page 134 at the beginning of this section. We're going to go into a little bit more detail on how zeros relate to some of those other terms and some of those other concepts. First, let's go ahead and talk about how zeros and factors relate. We have done a little bit of work on this already. So when it comes to zeros and factors, we already know how we get from a zero to a factor. We went through a couple of methods of doing so. We talked about the simple case when we have something like x minus 2. We said that we can just take the opposite of the item that is in this position. So if x minus 2 is a factor, then x equals 2 is a 0. We also talked about the fact that if we had something slightly more complicated like 2x minus 7, that we could use the zero product property. So if we know that 2x minus 7 were a factor of a quadratic and we wanted to know what value of x was the 0 that corresponded to this factor, we could just set the factor itself equal to 0 and solve for x, and we would get x equals 7/2. So 7/2 is the value of x that would make this factor equal to 0 and would therefore make the quadratic equal to 0, assuming that we had another linear factor over here. Let's say we did have another linear factor over here like x minus 2. We would know that our two zeros were x equals 7/2 and x equals 2. So we're going to run through a bunch of hopefully fairly simple examples right now that will illustrate how we get zeros from the factors. So example number 18, I would pause the video and try to do this one on your own. By this point in our discussion of quadratics and zeros, you should have no problem doing these on your own. For each of the following linear factors of a polynomial function, determine what root or 0 is associated with the factor. Example 18a is the simple case. We can just take the opposite of the number here, and we get that x equals 3 would be a 0 of this quadratic. The factor in 18b here, we're going to go ahead and use the zero product property in this case, so we will set that factor equal to 0. We will subtract the 2 from both sides. We get 3x equals negative 2. Divide by 3, we get x equals negative 2/3. Next, we have the factor 4x. Well, remember, we can also use the zero product property here. We can just set that factor equal to 0, divide both sides by 4, and of course we get x equals 0. So 0 is the root, or 0 is associated with the factor 4x. M minus x, again, why don't we use the zero product property here? Why don't we just set the factor equal to 0? We will add x to both sides. Remember, we want to solve for x, so I'm just isolating x on the right in this case. I get x equals m equals x equals m, same thing. And I know that here my root, or 0, is going to be m. So when x equals m, this factor will equal 0 because m minus m is 0. When we have a imaginary factor like we do here, x minus 2 minus I, best thing to do, zero product property. We're just going to set that factor equal to 0. We are going to isolate the x by adding the 2 and the I to both sides, and we are going to get x equals 2 plus I. So 2 plus I is the value of x that will make this factor equal to 0, and therefore would make the quadratic itself equal to 0, which is what zeros are all about. In terms of going in the other direction, in other words, going from your 0 to your factor, there's multiple ways that we can do this. One easy way to do it is, I'm going to go ahead and highlight this down here, is we just take the opposite of the 0 that's given and we throw an x in front of it. So in the case of a 0 like x equals, let's say, negative 4, we just take the opposite of that 0 and we throw an x in front of it. If we have a fractional 0, often what we need to do, so let's say we have x equals 3/2, we would take the opposite, we would throw an x in front, and then usually really depends on what the quadratic looks like, namely what your a value is in front of the x squared term, but usually you're going to have to swing the denominator of the fraction in your factor up in front of the x and then get rid of that denominator. In other words, usually when we see a 0 like 3/2, we are talking about the factor 2x minus 3. So that's generally the way that we can easily get from our factors to our zeros. At the top of the next page, we're going to do a few examples of getting to the factors from the zeros. So in example 19, you might want to do this on your own before I start going through it here. What linear factor is associated with each of the following roots? So what we are given here are zeros or roots, and we need the factor associated with the root. So in the case of example 19a, I am simply going to switch the sign on the -4, throw an x in front. With 0, switching the sign on 0 does nothing. It just keeps 0, so x plus 0, x minus 0, it doesn't really matter. My factor is going to be x. Now again, it could be that the factor is 4x or 2x or 7/2 x. A lot of this will depend on the actual quadratic, the actual equation for the quadratic. You know, if you have 2x squared versus 5x squared, well, that number in front of the quadratic term, your a value, a lot of times will help you see whether any of your factors need certain coefficients. X equals 3/2, I believe we did this exact example on the previous page or something very similar to it. So I'm going to switch the sign on the 3/2, and I am going to swing that 2 up in front of the x and then get rid of it, so I have 2x minus 3 here. In example 19d, x equals s, so again, switching the sign on the s, throwing an x in front of it, I get x minus s. With example 19e, again, flipping the sign on these guys and then throwing an x in front of them, x plus 1 plus 2i. And there is the complex factor, I suppose you would call it, associated with this 0. So that is how we move back and forth between factors and zeros. In terms of zeros, factors, and divisibility, this is definitely gets a little bit more advanced here, but probably the easiest way to look at how zeros, factors, and divisibility relate when it comes to a polynomial function is just to go back to basics, to go back to what you learned about factors when you were probably in, I don't know, 4th, 5th, 6th grade, something like that, where you learned that, for instance, if we say 3 is a factor of 12, that is exactly the same. That is equivalent to saying that 12 is divisible by, that says divisibly, I wanted divisible. 12 is divisible by 3. And by the way, that was also the same, since we're about to talk about zeros, factors, and remainders in another page or two, that was also the same as saying that when 12 is divided by 3, the remainder is 0. These are just 3 ways of saying the same thing. So for instance, if I start, I'm gonna add sort of one step over here. If I start with, x equals, let's keep it simple, let's say x equals 2 is a root or 0. Okay, we just talked about the fact that we could say x minus 2 is a factor of the polynomial. That also means that the polynomial, and when we say polynomial, we're talking about a function. So x minus 2 is a factor of, let's just call it f, a factor, I need 2 f's there, of f. And then we know that f, the polynomial f, is divisible by x minus 2. Again, just equivalent statements. And we would also know that when f is divided by x minus 2, by that factor, the remainder is 0. So again, just taking what we learned long time ago, probably in elementary school, about factors and divisibility and remainders, and we're just applying that information to some of the stuff that we have learned about functions, polynomial functions, their factors, their zeros, and so on and so forth. So when it comes to zeros, factors, and divisibility, by the way, all the stuff that we just ran through here is it's in the text here. If you feel like you need to read through this text, obviously you can pause the video and do so. Let's go ahead and do a few examples so that we can see how the chain of thought needs to go here. And do remember that when I say chain, I'm just talking about this chain. We've got the root, the 0, we've got the factor, we've got the divisibility, and then we've got the remainder. We're going to deal with remainders later. As I said, here we'll just be focusing on zeros, factors, and divisibility. So if you want to do example 20 on your own, obviously pause the video and then come back and join us. 20a, a parabola crosses the x-axis at 3, 0. The quadratic function corresponding to this parabola must be divisible by what linear factor? Okay, so you can see here we have an x-intercept. So that's where the chain starts, x-intercept. We know that the x-intercept is 3, 0. Well, remember, that means that x equals 3 is a root, or 0, right? We talked about that already in this section multiple times. And when we know that x equals 3 is a root, or 0, we know that x minus 3 is a factor. And remember that anytime we have a factor of some polynomial, that polynomial is divisible by that factor. So we know that if this parabola crosses the x-axis at 3, 0, x equals 3 is a root, or 0, and x minus 3 is a factor of this polynomial, and therefore this polynomial must be divisible by x minus 3 if x minus 3 is a factor of the polynomial. Next, we have 20b here. In the quadratic, f of x equals a bunch of stuff. C is a constant. If f of x is divisible by x minus 3, what is the value of c? Okay, so in this case, the chain seems to start at this note that f of x is divisible by x minus 3. So that leads us to x minus 3 is a factor, right? If f is divisible by x minus 3, then x minus 3 is obviously a factor. Just two equivalent statements. Same thing. Divisible by x minus 3 means x minus 3 is a factor. And what does that mean? That means that x equals 3 is a root or a 0. And that means, remember, definition of 0 is that when 3 goes into this function, in other words, when x is 3, we should get a 0 out. When 3 goes in, f of 3, the y value, will be 0, which means we can just take that 3 value for x, substitute it into the quadratic, and we know that we will get 0 out. And watch what happens when we do that. We get 3 squared plus 3 plus c equals 0, and now we have a nice simple equation that has only one variable, and we can solve for the value of that variable now. So we get 9 plus 3 plus c equals 0. That's 12 plus c equals 0. We subtract the 12, we get c equals negative 12. So we know that the value of c, which is what we are being asked here, is negative 12. c equals negative 12. In 20c, example 20c, we have the function f is divisible by x plus 2 and intersects the y-axis at y equals negative 1. What is the value of f of negative 2 minus f of 0? Okay, so we need the value of f of negative 2 minus f of 0. Okay, well, let's start with the divisible by statement. Remember, a function being divisible by x plus 2 means that x plus 2 is a factor. And x plus 2 is a factor means x equals negative 2 is a 0. And what that means is that when we take f of negative 2, when negative 2 goes in for x, we get out a 0. Well, that's nice, because that now tells us that this first part of what they are asking us, f of negative 2, that's just 0. And now we have to find out what f of 0 is. Well, let's take this next phrase here. It says that we intersect the y-axis at y equals negative 1. Remember, when we intersect the y-axis, I've said this a few times in this section, I believe, that when we intersect the y-axis, what is our x value? Our x value is 0. Anytime we are on the y-axis, our x value is 0. So we know that the point 0, -1 lies on this function. That 0, of course, is an x value. That -1, of course, is a y or f of x value. And putting this all together, we know now that f of 0, remember that's the x value, has to equal -1. When 0 goes in, -1 comes out. We now know that f of 0 is -1, so we are doing 0 minus -1 here, which equals 1. So the answer to 20C is 1. So again, that is how zeros and x-intercepts and factors and divisibility and those terms, that is how they all relate. And it really does help to make sure. You might even want to add the x-intercept to this chain up here. If our x-intercept is 2, 0, we know the root, we know a factor, we know what the function is divisible by, or at least one factor that the function is divisible by. We know that the remainder is 0. It really does help to make sure that you know all of the links in this chain. There are 4 or 5 of them that you should be aware of. Next, we are going to bring the idea of remainders into the mix. We've already sort of done that when we talked about the chain, the very last step in the chain here. We brought in the idea of a remainder. We have not seen, by the way, this is at the top of the next page here. We have not seen many or really even any questions that have dealt with remainders of polynomials or the polynomial remainder theorem. There was one question that showed up a long time ago. If memory serves me correctly, that question showed up on a test that was a sample test that College Board released in 2015 or 16 to give students an idea of what the quote-unquote new SAT would look like. So on the released administered tests, the official released administered tests, I don't believe we've seen anything about polynomials and their remainders and the polynomial remainder theorem. Is there a chance the College Board could test this stuff? Yes, which is why if you are going for a score well into the 700s, you should know this. If you are not going for a score well into the 700s, this is probably stuff you really don't need to worry about at all. So at the top of the page here, we really just reiterate the information that we talked about on the previous page. We iterate the idea of that chain where we go from 0 to factor to divisible by to remainder is 0. Example number 21 is really just going to require us to incorporate that very last step of the chain. The remainder is 0 step. So on example 21, if you want to try this, if you're feeling bold and want to try this question on your own, go ahead and do so. If the graph of g of x in the xy plane intersects the x-axis at -4, 0, what is the remainder when g of x is divided by x plus 4? I'm going to circle g of x divided by x plus 4. So the remainder when g of x is divided by x plus 4. So again, let's go through the chain. We have an x-intercept at -4, 0. Remember that our x-intercepts are exactly the same as our zeros or roots. So we know that this function g has a root of x equals -4. Let me get rid of this. This is ugly. We also know, therefore, that a factor of the function that we're dealing with here, function g, is x plus 4. Remember, I'm just taking the opposite of that root or 0, placing the opposite of that root or 0 here and slapping an x in front of it. So we know that g of x has a factor of x plus 4. That means that g is divisible by x plus 4, right? If x plus 4 is a factor of g, then g is divisible by x plus 4. And that means that when we divide this function g by x plus 4, because x plus 4 goes in evenly to g, because g is divisible by x plus 4, our remainder is going to be 0. They are asking us what the remainder is. There's our answer. Our remainder is going to be 0. Why will it be 0? Because we know that g of x is divisible by x plus 4, and anytime you divide something by something else, that top thing is divisible by, so a numerator, denominator. If this denominator goes evenly into the numerator, in other words, the numerator is divisible by the denominator, the remainder is always going to be 0. We know that g of x is divisible by x plus 4 because of all these other links in the chain, which means the remainder is 0. Now, that brings us to what is known as the polynomial remainder theorem. Again, I would not worry too much about the polynomial remainder theorem. We are simply going over this here because there is a very, very, very slight chance that College Board may decide to test something like the polynomial remainder theorem. There are proofs for the polynomial remainder theorem. We are not going over those proofs here. We do not need all that in-depth an understanding of the polynomial remainder theorem. We basically are just going to need to know what it is or how to apply it practically. The polynomial remainder theorem says that when you have a function, in this case we're talking about f of x, and that function is divided by some factor, this is a linear factor, type of factors we've been dealing with over and over again, that when we divide that function by that factor, the remainder will be found by plugging n, this value here, into the function. In other words, if we calculate f of n, we will be finding whatever the value of f of n is, that value will be the remainder when f of x is divided by x minus n. Practically, what does that mean? It means that if we are ever asked for the remainder when some function is being divided by some factor, we just take whatever that n value is, we plug that n value in for x into the function, and whatever value we get is the remainder. So, in number 22, we have a few examples on which we're going to use the polynomial remainder theorem. If you, again, are feeling bold and would like to do this on your own, go to it. I'm going to work through these right now. So, 22a, we get f of x, we get this quadratic function. What is the remainder when f is divided by x minus 1? Okay, so this is a pretty basic example. Remember what we said? We said that if we want to know what the remainder is when f is divided by x minus n, we just do f of n. Well, in this case, the n is clearly 1. They're in the same position, x minus n, x minus 1. So all we're going to do is we're going to do f of 1. We're just going to find out what f of 1 is. And when we do f of 1, what do we get? We get 3 times 1 squared, which is just 3, minus 4, which equals negative 1. There you go. That is going to be, that negative 1 is going to be the remainder when f is divided by x minus 1. 22b, the remainder when p of x is divided by x plus 2 is 3. What is p of negative 2? Well, let's take a look at this. If this guy right here is our x minus n, so I'm going to rewrite x plus 2 as x minus negative 2. So it should be pretty clear that our n is negative 2. Another way of thinking about that is that n is the 0. N is the 0 corresponding to whatever factor we're dealing with. And when we're dealing with a factor of x plus 2, we know that our 0 is going to, this is the simple case, we can just flip the sign on that positive 2 and we get the 0 of negative 2. So n is just whatever value your 0 would normally be, and in this case our 0 would be negative 2. So n is negative 2. So they are telling us that the remainder when p of x is divided by x plus 2 is 3, and that means that when this is a p, not an f, that means that when negative 2, the value for n, goes into the p function, we should get out 3, because when we evaluate p at the n value, we get out our remainder. Well, guess what, folks? The question is just asking us what is p of negative 2. We know that p of negative 2 is 3. That one's a little bit of a brain bender. Might take a couple times looking at that to have it all come together, but hopefully eventually it will all come together. C, 22c, what is the remainder? What is the remainder when f of x equals this cubic function is divided by 2x minus 3? Well, all we need to understand on this particular example is that nothing changes just because we have a higher degree polynomial here. The polynomial remainder theorem is it applies to all polynomials, quadratics, cubics, linear functions, all polynomial functions will abide by the polynomial remainder theorem. So all we have to do, once again, is find the 0 that is associated with 2x minus 3. That's what I was saying on the previous example. If we find the 0 that is associated with the factor 2x minus 3, we will get our n value. So I am going to use the zero product property here. So I get that x equals 3 halves. So that's going to be the n value. That's the value that is going to go into the function f of x in order to find the remainder. So if I do f of 3 halves, what I will find in my calculator, let me go ahead and do this, and I'm going to do this with the store function. So what I'm going to do is I am going to do alpha f1 enter 3 over 2. For those of you who have a TI-84, you should be able to do this exactly the way that I'm doing it. So I'm going to do store and then the X button and then hit enter. And now I am going to simply type all of this stuff into my calculator. Now I am going to do 2x cubed. I am going to subtract 5x squared and then minus x and then plus 6 and then enter. Look at that, 0. So the remainder when this function f is divided by 2x minus 3 is 0. And what that means, by the way, is that 2x minus 3 is a factor of this cubic function. Those are just 2 steps in the chain that we've been talking about. At the top of the next page, we're going to hammer this all home with one more example. In example 23, we are going to relate zeros, factors, divisibility, remainders as we've been doing. So for the function f, we've got one single cubic function here. F of x equals whatever. We've got to determine the following. So first, we need the remainder when f is divided by x plus 2. This is polynomial remainder theorem. Remember what we do? We take our n value, which is the 0 that is associated with this factor. We can also look at this as x minus negative 2. So the n is negative 2. We take that n value, we plug that n value into the function, and whatever value we get out is our remainder. Again, I'm going to do this wisely. This is a calculator question, so I am going to do negative 2. I'm going to store it. By the way, if you do not have the store function on your calculator, you're just going to have to plug in negative 2. You know, you can just type this into the calculator like this. You just got to make sure that you're putting parentheses around the negative 2 so you don't make any careless mistakes. I now have negative 2 stored in my calculator as the x value, so all I am going to do now is I'm going to do x cubed plus, got to get out of the exponent there, plus x squared minus 8x and minus 12. And what do I get? Oh, I get another 0. Okay, so I now know that the remainder, remember, that value that we get out when we plug the n value into the function, that value that we get out, in this case 0, is the remainder. So my remainder is 0. Now, all of these other questions simply deal with the chain that we've been talking about over and over again. So we just found out that when f is divided by x plus 2, our remainder is 0. That means that x plus 2 is, yes, a factor of f. It also means that f is divisible by x plus 2. And in the case of example 23D, this says the graph of f of x intersects the x-axis at 3, 0, and which other point. So we know that if x plus 2 is a factor, that's what I needed there, x plus 2 is a factor, then we also know that x equals negative 2 is a root or 0. And remember, roots or zeros are synonymous with x-intercept. So we know that this function will intersect the x-axis. It will have an x-intercept at negative 2, 0. So this example 23, it's a really nice example that sort of relates the remainder to the factor, to the divisibility, to the x-intercept and 0 idea. Let's take a look at how graphs might play into the concepts and terms we've been discussing over the last couple pages. In example 24, again, if you want to try it on your own, go ahead and do so. I'm going to put the calculator away. We do not use the calculator here. In example 24, we've got the graph of the polynomial function h is graphed above with x-intercepts as shown. Okay, I can see the x-intercepts. They are shown. They are labeled. What is the remainder when h is divided by 2x minus 1? Okay, well, again, we know that if we want to find the remainder when a certain function is divided by a certain factor, we can take the 0 associated with that factor, the n value. So that's going to be 2x minus 1. I'm going to set that equal to 0 to find the 0. So that's 2x equals 1 divided by 2 divided by 2. So we get x equals 1/2. That would be the n value here. By the way, in case you want to know another reason that the n value that we want to use here is 1/2. Remember I said you can just think of the n value as the 0 that is associated with this factor. However, you can also look at this and factor out a 2. And what you get is this. You get x minus 1/2. So x minus 1/2, you can see that the n is 1/2. So if you want to think of it that way, you can. I think it's a little bit easier actually just to think of n as the 0 value, the value of x that would be the 0 associated with this factor. So what I'm going to do, that is now my n value. I'm going to look at the graph and I'm going to see that when x, or our n value, is 1/2, in other words, when 1/2 goes into the function, right, that's an x value, what comes out is 0. And we need to understand that when it comes to graphs and function notation, saying something like 1/2 comma 0, in other words, writing this ordered pair, this pair of coordinates, is no different from writing this. Those are exactly the same thing. This is an x value here. This is a y value here. So writing the coordinate 1/2 comma 0 is no different from saying that we've got this function. This technically should be an h, not an f. We're dealing with an h function here, not a big deal. But when 1/2 goes into the h function, then 0 comes out. And what that means is, once again, because we plugged in the n value here and got out a 0, remember that 0 is the value, that's the value of the remainder, which means our answer here is 0. The other way of looking at this would have been to immediately convert, this might even be an easier way, immediately convert this x-intercept into a factor by knowing that x equals 1/2 has to be a root or 0, which means that x minus 1/2 has to be a factor. Remember that we said we will often need to take that 2 in the denominator and swing the 2 up in front of the x, leaving us with 2x minus 1. So 2x minus 1 is a factor. That means that h is divisible by 2x minus 1, and that means that the remainder equals 0 when h is divided by 2x minus 1. And that's what the question is asking. What is the remainder when h is divided by 2x minus 1? So you can do this in either way. There's really no difference between these two ways. They're just a slightly different approach. But again, you know from your x-intercepts here, you know your zeros, you know your factors, you know your divisibility, you know your remainders. So the remainder is 0 on number 24 here. That is how zeros and factors and divisibility and remainders relate. I do really suggest that you look hard and often at the chain of ideas that we talked about a couple pages ago. This chain of ideas. Keep in mind also that on the second page of this section, back in an earlier part of the quadratics section and in an earlier video, we did talk about all of those terms that are synonymous with zeros and roots. It is really important that you understand the relationship between all of those synonymous terms.